What if the universe's deepest secrets are hidden in shapes we could barely even imagine?
Hmm.
Today, we're diving into the world of Calabi-Yau manifolds.
Oh.
These complex, multidimensional objects are not just mathematical curiosities.
Right.
They're central to string theory,
Uh-huh.
a leading candidate for a theory of everything,
Okay.
potentially unlocking the universe's fundamental structure.
It's fascinating how these manifolds bridge abstract mathematics with our physical reality.
Okay, so let's break this down.
Yeah.
What exactly are Calabi-Yau manifolds, and why should we care?
Oh, well.
Imagine a universe with more dimensions than we can perceive.
Right.
These extra dimensions, according to string theory, need to be hidden somehow.
Yeah.
That's where Calabi-Yau manifolds come in. They
Uh-huh.
provide the shapes for these hidden dimensions,
Okay.
curled up in incredibly intricate ways.
Think of it like origami,
Oh,
but on a cosmic scale.
okay.
The way these dimensions are folded determines the fundamental properties of our universe.
So they're like the blueprint of reality.
It's hidden in the folds of these bizarre shapes.
Exactly.
Okay.
But there's a catch.
Okay.
These shapes can't just be any random folds.
Yeah.
They had to be perfectly balanced in a way that physicists call Ricci flat.
What does Ricci flat even mean?
It's a mathematical concept that describes a space with no curvature.
Okay.
Think of a perfectly inflated balloon.
Okay.
No part is stretched or squeezed more than any other.
Right.
That's essentially what Ricci flatness means,
Okay.
but in multiple dimensions.
So these Calabi-Yau manifolds are like perfectly smooth,
That's a good analogy.
multi-dimensional balloons.
But there's another crucial property,
Holotomy.
holonomy.
Okay.
Imagine a spinner that can only rotate in specific symmetrical ways,
Okay.
like the gears in a perfectly crafted clock.
Huh.
That restricted rotation is what SUN holonomy represents. It governs how things can spin within these hidden dimensions.
Okay, my brain is starting to hurt, but in a good way.
Yeah.
So we have these complex,
Yes.
perfectly smooth shapes. Right.
With restricted rotations. And they're the key to understanding hidden dimensions.
Precisely.
Wow.
And these shapes are described by some truly beautiful mathematical equations.
Uh-huh.
One famous example is the quintic hypersurface,
Okay.
defined by the equation x0 plus x0 plus x0 plus x0 plus x0 equals 0.
5 terms, each raised to the 15th power, all adding up to 0.
Yes.
What does that even mean?
Think of it as 5 lumps of clay.
Okay.
But instead of regular clay, it's complex clay, meaning it has extra dimensions. The equation tells us how to arrange these lumps so they perfectly cancel each other out in this higher dimensional space.
Wow.
That precise cancellation creates the unique properties of this particular Calabi-Yau manifold.
This is seriously blowing my mind.
Yeah.
So we have this quintic hypersurface as one example.
Yeah.
But there are countless other Calabi-Yau shapes out there,
Absolutely.
each with its own unique properties.
And what's even more fascinating is the concept of mirror symmetry.
Mirror symmetry. Our sources mention something about Hodge numbers being involved.
Yes, Hodge numbers essentially count the holes of different dimensions in these shapes.
Okay.
The amazing thing about mirror symmetry is that it swaps these Hodge numbers between the two mirror partners. If one shape has a lot of holes of a certain type, its mirror will have an equal number of a different kind of hole. It's like nature balancing itself out.
Right.
Even in these abstract, multi-dimensional realms.
So studying one Calabi-Yau shape is like getting a 2-for-1 deal.
That's a great way to put it.
You automatically learn about its mirror partner as well.
And this mirror symmetry has profound implications for physics.
Okay.
It suggests that seemingly different physical theories might actually be describing the same underlying reality just from different perspectives.
Hold on. Are you saying that there could be multiple versions of string theory, all describing the same universe but using different Calabi-Yau shapes?
It's a mind-boggling concept, but that's what string dualities suggest. And this is where the study of Calabi-Yau manifolds gets really exciting. They become the playing field for exploring these dualities, potentially leading us towards a unified understanding of the universe.
Okay, I need a minute to process all of this.
Yeah.
We've got these mind-bending shapes,
Right.
hidden dimensions, mirror symmetry,
Yeah.
and the possibility of multiple versions of reality all intertwined. It's like the universe is playing a cosmic game of hide-and-seek with us.
That's a great analogy.
And Calabi-Yau manifolds are the clues.
And we've only just begun to explore these clues.
Okay.
But before we go any further, let's take a step back and talk about how we even know these shapes exist.
Good point. We've been talking about them as if they're real, tangible objects.
Right.
But they seem so abstract.
Yeah.
How did mathematicians even come up with this idea?
It all started with a conjecture.
Okay.
A bold mathematical statement proposed by Eugenio Calabi in the 1950s. He suggested that certain types of abstract spaces,
Now known as Calabi-Yau manifolds,
right,
could exist with a very special property, Ricci flatness. But proving his conjecture was a monumental task.
So Calabi said these shapes could exist, but it took decades to actually prove it.
Exactly. It wasn't until the 1970s that Yau provided the rigorous mathematical proof, solving complex partial differential equations to demonstrate the existence of these Ricci flat metrics.
Wow.
It was a major breakthrough, earning Yau a Fields Medal, the highest honor in mathematics.
Wow. Solving those equations must have been incredibly difficult.
It was a tour de force of mathematical ingenuity.
Right.
It's like finding a needle in a cosmic haystack.
Yeah.
Proving that these incredibly specific, perfectly balanced shapes can actually exist in the vast landscape of mathematical possibilities.
This is why I love these deep dives.
Right.
We start with these seemingly abstract mathematical concepts.
Yeah.
And they end up having profound implications for our understanding of the universe.
It's true.
But I'm sure there's more to this story.
What other fascinating aspects of Calabi-Yau manifolds did you uncover?
Well, there's the question of what happens when these smooth shapes develop singularities,
Yay.
points where they pinch together. Imagine a perfectly smooth balloon suddenly developing a sharp point.
Right.
These conifold singularities, as they're called,
Okay.
are described by surprisingly simple equations like xi(CW equals 0.
So it's like these seemingly simple equations are hiding glitches in the fabric of space-time. What happens at these points? Do
Well,
they tear the universe apart?
not quite.
Oh.
These singularities can actually represent connections between different parts of the Calabi-Yau landscape, almost like tunnels or gateways between different regions of space-time.
Wait, are you saying these glitches could be portals to other
This
dimensions?
is one interpretation.
This is getting wilder by the minute.
These conifold singularities challenge our conventional understanding of space and time,
Right.
forcing us to grapple with the deep implications of string theory and its potential to reshape our view of reality. Okay.
There's even more to explore.
Okay, my mind is officially blown.
Yeah.
Perfectly smooth shapes with glitches that might be portals to other dimensions, all hidden within the folds of space-time.
Right.
This is incredible.
And it gets even deeper.
Oh, no.
We also have to grapple with concepts like the complex Monge-Ampere equation.
Okay.
It's a powerful mathematical tool used to find the perfect shape or metric for these manifolds,
Right.
ensuring that they meet the stringent requirements of being Ricci flat.
I have to admit that equation sounds intimidating.
Yeah, it can be.
Can you break it down for us?
Think of it like using a special mathematical tool to smooth out the wrinkles in a multidimensional fabric.
Okay.
This tool, the complex Monge-Ampere equation, ensures that the Calabi-Yau shape fits perfectly within the framework of string theory.
So it's like ironing out the kinks in the fabric of reality to make sure these Calabi-Yau shapes are perfectly smooth.
Exactly.
This is why I love these deep dives.
We start with abstract equations and end up talking about the very structure of the universe.
And there's so much more to uncover.
I bet.
Next, we'll explore how these manifolds bridge the gap between abstract math and the physical world,
Okay.
especially through their application in enumerative geometry. It's a fascinating field that essentially involves counting things within these multidimensional shapes.
Counting things in multiple dimensions.
It's a wild concept, but it has profound implications for understanding string theory and how it connects to the observable universe.
Okay.
We'll dive into all of that after a short break.
Okay.
Stay tuned.
Okay.
Welcome back. Now that we have a better understanding of what Calabi-Yau manifolds are,
Right.
let's explore how they actually connect to the physical world.
Okay.
One of the most exciting links is through a field called enumerative geometry.
Enumerative geometry.
Yeah.
That sounds pretty intimidating.
It can be.
Is it as complex as it sounds?
But at its heart, it's about counting things. Specifically, we're counting curves embedded within these Calabi-Yau spaces.
Okay, so we're not talking about counting apples and oranges here.
No.
What kind of curves are we counting in these multidimensional shapes?
Imagine drawing loops on a donut. You could have a simple loop around the outside or a more intricate one that winds through the hole.
Right.
In Calabi-Yau manifolds,
Mm-hmm.
we're counting similar loops,
Okay.
but in much higher dimensions.
Okay.
These counts are known as Gromov-Witten invariants.
So instead of donuts, we have these mind-boggling Calabi-Yau shapes. And we're
Yes.
counting all the different ways you can draw loops within them.
Exact.
What does that have to do with physics?
These Gromov-Witten invariants give us information about the probabilities of different string interactions. Remember, string theory proposes that the universe is made up of tiny vibrating strings, and these strings can move and interact in various ways within these Calabi-Yau spaces.
So the shape of the Calabi-Yau manifold actually influences how strings behave. That's wild.
The geometry dictates the physics.
Wow.
It's a profound example of how abstract mathematical concepts have tangible consequences for our understanding of the universe.
This is blowing my mind. We've gone from these abstract shapes to counting loops within them?
Right.
And now we're talking about the behavior of strings in the universe.
Yes.
It's like connecting the dots in a cosmic puzzle.
Exactly.
Wow.
And there are even more dots to connect.
Okay.
Calabi-Yau manifolds also play a crucial role in string dualities.
Okay, here we go again.
Yeah.
More complex terminology.
It's true.
What are string dualities?
Imagine looking at a painting from different angles.
Okay.
The colors and shapes might appear different depending on your perspective, but it's still the same painting.
Right.
String dualities are similar. They suggest that different versions of string theory, which seem distinct at first glance, might actually be describing the same underlying physics from different viewpoints.
So it's like different versions of string theory are just different perspectives on the same universal truth?
That's the idea.
Okay.
And Calabi-Yau manifolds are essential to this concept.
Right.
Different string theories, when compactified on specific Calabi-Yau manifolds, can give rise to the same physics.
Yeah.
For example, type IIA string theory on one Calabi-Yau manifold can be physically equivalent to type IIB string theory on its mirror partner.
There's that mirror symmetry concept again.
Yes.
It's amazing how everything seems to connect back to this idea of duality. But why are these string dualities so important to physicists?
They offer a glimpse of a deeper level of understanding, a unified framework that might underlie all the different versions of string theory.
Okay.
It's like searching for the Rosetta Stone of the cosmos.
Wow.
Trying to decipher the universe's grand unified theory.
This is seriously mind-boggling.
It is.
But let's not forget about those conifold singularities we talked about earlier. Do those glitches in space-time cause any problems for string theory?
They certainly introduce complexities.
Okay.
These singularities can lead to fascinating physical phenomena. For example, they might be responsible for the emergence of new massless particles.
Wow.
And they could even provide a way for the manifold to transition between different topologies.
Hold on a second. Are you saying these singularities could be like tunnels connecting different cosmic landscapes? Could they allow travel between different parts of the universe or even different dimensions?
It's a fascinating possibility, but it's still an area of active research.
Right.
These conifold singularities push the boundaries of our current understanding of space and time, forcing us to grapple with the truly mind-bending implications of string theory.
Okay, my head is spinning.
Yeah.
This is more complex and more exciting than I could have imagined.
It is.
And there's even more to delve into.
Yes.
We haven't even touched upon the mathematical tools used to navigate these complex landscapes. For example, there are Picard-Fuchs equations, which describe how certain mathematical properties of Calabi-Yau manifolds change as we adjust their parameters.
It's true.
Okay, you lost me a bit there.
Yeah.
Picard-Fuchs equations.
Yeah.
What are those all about?
Imagine measuring the lengths of different loops within the Calabi-Yau manifold.
Okay.
Those lengths are essentially the periods.
Okay.
The Picard-Fuchs equations provide a way to track how these lengths change as we adjust the parameters that define the manifold. It's like having a map that guides us through the complex landscape of Calabi-Yau spaces, showing us how they can transform and connect in unexpected ways.
So it's like a mathematical GPS for navigating these multidimensional spaces.
It is.
That's pretty cool.
And this exploration is far from over.
Right.
Physicists and mathematicians are still working tirelessly to classify and understand the full spectrum of Calabi-Yau manifolds, to uncover their hidden symmetries, and to probe their implications for everything from particle physics to cosmology.
It sounds like we've just scratched the surface of this vast and intricate world.
We have, but that's what makes it so exciting.
Right.
Every new discovery about Calabi-Yau manifolds opens up new avenues of inquiry, new possibilities for understanding the universe and our place within it.
Before we wrap up, I want to make sure I understand the significance of all of this.
Yeah.
We've gone on this incredible journey through abstract mathematical concepts,
Yes.
explored their connections to string theory,
Uh-huh.
and even glimpsed the potential for hidden dimensions and cosmic turtles. But what does it all mean for us?
That's the ultimate question.
How does this knowledge impact our understanding of the universe and our place within it?
Calabi-Yau manifolds, while rooted in advanced mathematics,
Right.
are ultimately tools for understanding the physical world.
Okay.
They offer a framework for exploring the fundamental nature of space-time and the forces that govern the cosmos.
So it's not just about equations and abstract shapes.
No.
It's about connecting those concepts to the reality we experience.
Yes, exactly.
Now let's understand the connection.
Think about the idea that the universe might have extra dimensions curled up and hidden within these Calabi-Yau shapes. That has profound implications for how we think about gravity-particle physics and even the origin of the universe itself.
It's like realizing that the world we perceive is just the tip of a cosmic iceberg with vast hidden depths that we're only beginning to explore.
That's right.
But how do we even begin to study something that's inherently beyond our perception?
That's where the power of mathematics comes in.
Okay.
It provides the language and the tools to probe these hidden realms, to make predictions and test our theories. The study of Calabi-Yau manifolds has led to incredible breakthroughs.
Okay.
From the discovery of mirror symmetry to the development of sophisticated techniques for counting curves within these spaces.
It's amazing to think that we can quantify something so abstract, something that exists in multiple dimensions beyond our perception. But it makes sense. Math is essentially a way of describing the universe.
It is.
Right.
And those quantifications have real physical meaning.
Okay.
They offer insights into the probabilities of different string interactions, the types of particles that might exist, and the forces that govern their behavior. It's like we're cracking the code of the universe one mathematical equation at a time.
It's an incredibly humbling thought.
Yeah.
But where does it all lead?
Right.
What are the ultimate goals of studying Calabi-Yau manifolds?
One of the most ambitious goals is to find a unified theory of physics.
Okay.
A theory that reconciles quantum mechanics with general relativity. String theory, with its reliance on Calabi-Yau manifolds,
Right.
is a leading candidate for achieving that unification.
So we're searching for the holy grail of physics,
Yeah.
the theory of everything.
Huh.
And these intricate multidimensional shapes might hold the key.
They might. By studying the properties of these manifolds, the ways they can be connected, and the physics that emerge from their unique geometries,
Right.
we hope to gain a deeper understanding of the universe at its most fundamental level.
It's a mind-blowing prospect.
Yeah.
And even if it doesn't lead to a unified theory,
Right.
just thinking about these possibilities has been awe-inspiring.
It is.
I feel like I've gained a whole new perspective on reality.
That's the beauty of scientific exploration.
Right.
It challenges our preconceived notions and expands our understanding of the universe and our place within it.
I'm so grateful for the opportunity to dive deep into this topic with you.
Well, thank you.
It's been a truly enlightening experience.
I appreciate that.
As we conclude this deep dive,
Yeah.
what final thoughts would you leave our listeners with? What should they take away from this incredible journey?
Well, I think that's a great question to leave everyone with.
It really has been an incredible journey. We started with these abstract mathematical shapes, and now we're talking about the potential for a unified theory of physics
Yeah.
and a whole new understanding of reality.
It's amazing.
It's amazing how something so complex can be so captivating.
It is, and that's what I hope your listeners will take away from this deep dive.
Yeah.
A sense of wonder and a renewed appreciation for the power of human curiosity.
Absolutely. We've only just scratched the surface of Calabi-Yau manifolds.
Right.
But even that glimpse has been enough to inspire a lifetime of exploration.
It's a journey that requires a shift in perspective, a willingness to embrace the abstract, and to see the connections between seemingly disparate fields.
It's about recognizing that mathematics is not just a tool for calculation, but a language for describing the universe's deepest secrets.
Right.
And it's about the awe-inspiring realization that we as humans have the capacity to explore these realms,
Yeah.
to push the boundaries of knowledge, and to ask questions that might have seemed unfathomable just a few generations ago.
And what's truly exciting is that this exploration is still in its early stages.
Right.
Every new discovery about Calabi-Yau manifolds opens up new avenues of inquiry, new possibilities for understanding the universe and our place within it.
It's a journey filled with challenges, but the rewards are potentially immeasurable.
That's true.
I think that's a perfect note to end on.
Yeah.
To our listeners, we encourage you to continue this journey,
Mm.
to delve deeper into these concepts and to let your imagination soar as you contemplate the elegant geometry that might be underpinning the very fabric of reality.
I like that.
Until next time, keep exploring.
Yeah.
Keep questioning.
Absolutely.
Keep diving deep.
Dive deep.